Hello everybody, my name is Hafiz. I'm an academic medical physicist from the Advanced Medical and Dental Institute of University Science Malaysia. In today's workshop, I'll be covering the quality assurance aspects of daily implementation of image-guided radiation therapy, focusing on the use of cone beam CT imaging system. Before I continue with my presentation, I would like to acknowledge my fellow colleagues for their contribution in the materials that will be presented in these slides, my postgraduate students in the Institute for compiling some of the QA results and their assistance with the QA, University Science Malaysia and Ministry of Education Malaysia for the research funding being used to develop the in-house QA software that will be presented at the end of this presentation. This is my disclaimer slide. I have no financial interest in any of the radiotherapy and imaging technology reported in this presentation. My talk will consist of three main components. The first one is an introduction on the uncertainties in radiotherapy. Then I'll cover the overview of quality assurance program as well as the practical implementation of the quality assurance test for cone CT-based image-guided radiotherapy linac. As what have been presented in the previous sessions, we have come a long way since the 2D era of radiotherapy. Using CT and MRI, it is possible to determine the location and extent of a tumor more accurately. Also, now we have various conformal radiotherapy techniques that would allow dose distribution to conform tightly to the PTV and limit radiation dose to critical organs. And with IGRT, we are able to reduce the PTV further and allow for dose escalation or further hypofractionation. The accuracy is important in order to achieve the desired tumor control while maintaining toxicities to normal tissues to the minimum. In this ICRU report back in 1976, it was stated that an accuracy level of 5% is acceptable. However, further on in the report, it was stated that a dose accuracy level of 2% is desirable, but during that time it was impossible to achieve such standard. Moving to the current technology in the modern era of radiotherapy, where we have MRT techniques and IGRT systems available in the clinics, the question now is whether the current advances in radiotherapy are these accuracy endpoints up to 2% difference is achievable and can be improved, and how we can ensure that the minimum dose discrepancy can be achieved with comprehensive quality assurance process. With the recent development, IA has come up with the new guidelines on accuracy requirements and uncertainties in radiation therapy in order to promote awareness and encourage quantification of uncertainties to promote safer and more effective patient treatments. In the report, the concept of AARA is introduced, in which is known as accurately as reasonably achievable, where each center should have their own accuracy level based on their practice and also technology available at their clinic. With image-guided radiation therapy, we are able to estimate the interfraction and intrafraction errors, and then we can minimize and manage them. And these uncertainties that was measured from the patients can be included as one of the uncertainties in the PTV estimation. For example, in this illustration, we're going to deliver dose prescribed at 95% to the PTV volume. When there is a shift in the PTV, for example, due to immobilization shift of the patient or the motion of the tumor itself of 1.5 mm, as well as patient setup error of 0.5 mm, this caused a total of 2 mm shift of the PTV. However, you can see here the clinical target volume because of the PTV expansion of 3 mm. It is still within this dose at 95% irradiation area. This shows how image-guided radiation therapy can minimize and manage uncertainties during radiotherapy treatment. However, it is important to monitor the linear and imaging uncertainties. For example, the sagging of the couch, misalignment of the laser, the coincidence between the imaging and treatment of the center. So for example here, we illustrate when laser is misaligned by 2 mm. So you can see the total shift of the PTV is now 2 plus 2 mm, which is 4 mm. And that is bigger than the margin given, which is 3 mm. So you can see there's a 1 mm area that is not irradiated by the treatment. So the quality assurance program is used to quantify and monitor these linear and imaging uncertainties so that such laser misalignment that was illustrated in this example doesn't happen. And if it happens on the linear, it can be quantified and corrected by the linear service engineer before it's affecting patient treatment. To have an effective QA program, it should comprise of a QA committee that is multidisciplinary and oversees the entire QAP. It should also have manual of policies and procedures that is clear and concise and carried out in the department and reviewed and updated regularly. It should also have QA team that include all disciplines with well-defined responsibilities. And the goal of QA program for LINAC is to ensure that the machine characteristics do not deviate significantly from the baseline values acquired at the time of acceptance and commissioning. For QA test for LINAC, we have AAPM TG142 as our main reference. And also we have national guidelines from the Malaysian Ministry of Health from the Radiation Safety Division. However, TG142 does not cover the methods for performing the QA test and a few specialized equipment and techniques such as the following. The QA test of an IGRT LINAC can be arranged systematically according to the components of the LINAC. For example, the general safety aspects, the dosimetry mechanical aspects, the multi-leaf collimators, as well as the image-guided radiotherapy devices. And these components can be scheduled accordingly in daily occurrence or weekly, monthly, and annually tests, and as well as whenever required after maintenance by the LINAC service engineer. This is an example scheduling from my institute. So the QA tests are grouped into daily, weekly, and monthly tests that cover all aspects of quality assurance tests recommended by APM TG142 reports and associated documents. So we can see here there's also the estimate time and also the how regular each of these tests are performed. So we have daily, weekly tests that covers all aspects required according to TG142. We also have monthly tests that is actually performed separately for the dosimetry aspect, the mechanical aspect, the multi-leaf collimators, and also the imaging aspect, as well as the image-guided radiotherapy registration. And we also estimate the timing for calibration and also patient-specific dosimetry. Another important aspect in QA is the tolerances and action levels. So once we perform the QA, we'll get the magnitude of the uncertainty, and with that value, we will determine the next action plan. Okay. So for example, level 1 is the inspection action level, meaning that if the magnitude is actually within level 1 tolerance, it requires further investigation, but the radiotherapy treatment continues. Usually it is not a critical requirement but can lead to improvement in the QA program. This can happen from deviation due to changes in the personnel, the setup of the measurement, also the maintenance event. And typically level 1 is a value that is not exceeding the tolerance value. We also have level 2, which is the scheduled action. So it requires action to be scheduled in a few days. So usually the tolerance is close to the border of the value, and it will not have significant impact to radiotherapy over a few days. So that's why it is susceptible to action, to schedule the action in the next few days. We also have level 3, which is the stop treatment action or immediate action level. Okay, so meaning that the treatment has to be stopped and correction action should be made before the treatment can resume. So for example, this action level is the non-functional safety interlock or the dosimetry tolerance exceeding the tolerance, right? For example, if you set the uncertainty of the linear output to be 3% and it exceeded 3%, so the treatment should be stopped and immediate action should be taken to correct the high error. Okay, so how do you define these action levels basically, right? So it is actually based on your data set in the department, and it can be developed over time. So once you have performed enough QA at your department, you can come up with your action levels based on the values that you got. Okay, so it is an evolving value based on your QA data, and the usually level 2 and level 3 action levels are also set by the QA committee. So it is important so that everybody aware of this magnitude acceptable for the uncertainty, and will actually inform the person in charge of the QA when that happens. For the parameters measured, the acceptable tolerance should follow the AAPMTG 142 requirements, whereas the actions to be taken, if any of the parameters exceeded tolerance value, is uh, based on the institution action levels. Okay, so for example here, this is an example from my own institute. So we have action level 1, in which patient treatment is continued and the physicists are informed, and the physicists will investigate further and troubleshoot the problem by the next monthly QA. Action level 2, the same, patient treatment is continued and the physicists are informed. However, the physicists will investigate further and troubleshoot the problem within 1 or 2 working days. Okay, whereas for action level 3, the patient treatment is halted and the physicists are informed, and the physicists should investigate further and troubleshoot the problem immediately. And if the investigation and troubleshooting did not improve the error to be within tolerance, the physicist will notify the engineer to perform the maintenance check and repair. So the daily test includes parameters that can affect the dose to the patient by either dosimetry or geometric means. So dosimetry is usually referring to the beam output constancy, whereas geometry is referring to the lasers, optical distance indicator, and also the field size. It also includes audio-visual monitoring of the patient and also the interlocks. And usually it is performed during the morning warm-up of the linac and performed by the therapist. So the therapist and the medical physicist should have a well-defined policy and procedure to follow if any of the tests are found to be out of tolerance. These are the list of the daily tests performed for the dosimetry aspects, mechanical aspects, as well as the safety aspects of the linac. Okay, so you can see here the tolerance value acceptable for non-MRT system, or the MRT system, or the stereotactic or stereotactic body radiation therapy system. So you can see for the output, the acceptable tolerance for APMTG 142 is daily, but for electron is weekly. And this is different to our national guideline, which is only weekly tolerance at 2%. Whereas, for example, for the mechanical tolerance, you can see the value is different between non-IMRT, IMRT, and stereotactic treatment techniques. So, meaning that if your department is doing stereotactic on a daily basis, so it should actually have a laser localization within 1 mm. Whereas if you're only doing IMRT, then your tolerance level acceptable is 1.5 mm. So it varies depending on the type of techniques that you deliver using the Linux. So it's more stringent for more conformal beam and less stringent for less conformal beam. And the rest, like the safety aspect, usually is either functional or not. So if the door interlock is functional, then you can take that. But if it's not, then it is a level 3 action level, which you need to stop the treatment unless you've got the interlock fixed. So the monthly tests are designed to catch errors that have lower likelihood of happening daily or changing over a month. So this includes the tray position check, the beam profile constancy check, uh, as well as the imaging aspect of the cone beam CT. So these are the tests that is carried out monthly, and usually these tests are more involved, more technicals, and generally performed by the medical physicists. So these are the tests that should be carried out monthly for the dosimetry aspects. This includes the photon and electron output constancy, as well as the dose rate of constancy, the backup monitor check, the beam profile, and the wedge factor. So these are performed monthly, and the output should actually be within this tolerance level. Beside those, the mechanical aspect is also important because it affects the geometric accuracy of the treatment delivery. So this includes the light versus the radiation field coincidence for asymmetric and symmetric fields, the gantry and collimator angle indicators, the trace, the jaw position indicator, the crosshair centering, the touch position in the lateral longe and rotational position, then other mechanical aspects that you can see here. And these are the tolerance levels acceptable for each of these components. And these are the tests for the multi-leaf collimators. Some of the tests should be performed weekly, and some others should be performed monthly, and these are the acceptable tolerance level. The QA for the image-guided radiotherapy aspects can also be scheduled daily, weekly, monthly, and annually, and according to the modalities available at the clinic. So most centers would have at least the EPIT imaging, which is the mega voltage planar imaging. But nowadays, most centers would have the cone beam CT system, which is attached to the gantry, and it can do both planar and also 3D CT imaging. So the components of the QA can also be divided into these aspects, which is the imaging / treatment beam isocenter, which is the mechanical aspect, as well as the image quality and also the imaging dose aspect. So in terms of the frequency of the test I've mentioned earlier, the operation and functionality test as well as the collision interlock are performed daily. So these are important safety aspect. For example, the collision interlocks, if it doesn't work, then it's going to probably hit the patient when it's rotating around the patient. And also some centers do perform the daily registration test daily as well using a simple test phantom. Whereas the more stringent registration tests using ball bearing and also the image quality test, they are performed less frequent. It can be either monthly, quarterly, or annually. And also these tests are performed by the medical physicist because they need to assess the accuracy level of this component as well as the impact on the treatment to the patient. So this is the components of the QA test for the EPID imaging or the portal imaging device system. So for the collision interlocks, it needs to be checked whether it's functional daily. For the imaging and the treatment coordinate coincidence, for one of the gantry angle usually is at 0. This is tested to be within 2 mm for non-SRS or SPRT treatment, but if your center is doing SRS or SPRT treatment, the accuracy should be within 1 mm and it should be performed daily. For positioning and repositioning of the patient, also similar magnitude and should be performed daily. Whereas for the imaging and treatment coordinate coincidence at all the four coordinate angles, which is 0, 90, 180 to 70 degree rotation, similar magnitude, but this is suggested to be performed monthly by APM TG142. There's also the scaling of the images should be within 2 mm for both types of techniques of the treatment and should be performed monthly. So beside that, we also test for the image quality, and the reference is actually the baseline of the imaging system. So these are the values that we obtain during commissioning of the system that is actually should be within the performance accepted by the manufacturer, and we reviewed the value from our QA test compared to that value that we get from the commissioning, and this is performed monthly. And there are tests that only need to be done annually, for example the dose and also the range of the STD travel of the detector, but probably this is not relevant for a fixed EPID imaging system, for example in an Electa EPID. For planar KV imaging, the components are similar to EPID system, except that there is a test to check for the beam quality or energy, because now the radiation is coming from the X-ray tube compared to EPID is coming from the linac itself. So for the cone beam CT system, either using kilovoltage X-ray or megavoltage beam from the linac. So these are the components that need to be tested, as well as the accuracy level acceptable. So in terms of the imaging and treatment coordinate coincidence, so SRS or SPR technique requires accuracy of 1 mm, and this is a bit loose when if your center is just doing non-SRS or SBRT treatment. Positioning and repositioning both should be within 1 mm. Geometric distortion should be within 1 mm for SRS technique, and loosen a bit for non-SRS technique, and the rest, the image quality aspects, they are compared to the baseline that is measured during the acceptance testing. The image quality need to be performed monthly, whereas the imaging dose is recommended to be performed annually. So over here is the illustration of the imaging treatment beam isocenter concept. So as shown in this figure, the isocenter is the point in the middle of the linac rotation. So we have the collimator rotating to around this axis, the gantry also rotating around this axis, meaning that the gantry here is always at the same distance from the isocenter, as well as the table is also rotating around this point. So we need to check the treatment beam isocenter, which is this rotation point, is the same point as the imaging isocenter, meaning that when you perform the imaging, the center of the images is actually the same as the isocenter of the treatment. And we also match this isocenter with the laser reference in the room. So in order for us to check this imaging treatment beam isocenter accuracy or coincidence, so we actually use one of the phantom that we can use is this cube phantom, in which it has a radio opaque marker at the center of the phantom, and around the phantom we have this marker in which we can position the isocube at the center of the uh, isocenter, sorry, at the isocenter, whilst actually positioning it against the laser position, right? So when you position this cube according to the laser position, the radio upper marker should be at the center of the treatment. And when we image the isocube, this center of this radio opaque marker should also match with the center of the imaging. And when we register the two and we check the difference, so that then we get the imaging treatment beam isocenter coincidence. This is an example of the results from the institute for the monthly cone beam CT imaging isocenter. It is interesting to see in the first 3 quarters of the year, since after commissioning of the LINAC and the use of the LINAC for patient, the uncertainty in the first 9 months, they are all within 0.5 mm, so they are always very close to the isocenter. However, after that, we can see it started to increase, so the errors started to become larger and even exceeded 0.5 mm after about a year. And also after a few months, we noticed that there are some deviation that exceeded in one of the axis that exceeded 1 mm. So this 1.2 mm error, when we investigated further after we reported to the engineer, it was due to the experimental error, and those are not actually not an issue. But however, we can see that the errors has actually significantly become larger after a period of 1 year. So this is something that we need to monitor closely as the time goes, right? So I think the probability of the errors getting higher becomes larger when after a certain number of years of the net being used, and it needs to be monitored regularly after that. And also these tests are done using the ball bearing system, not the simple IsoCube device shown earlier, because that device is, because the ball bearing device is more appropriate for monthly tests. Uh, Also, it is also, as you can see, is also prone to error, experimental error, and may gives you false alarm in terms of the accuracy level. For the treatment isocenter test, you can see similar trend where the accuracy level becomes lower as the time progress, and also the values are actually higher compared to the imaging isocenter accuracy. Um, this is mainly this test is done using the electronic portal imaging device. Um, and we can see that there are times when it exceeded 1 mm value, but it is not consistent. So sometimes it actually happen randomly and will actually improve in the next evaluation. And this is the difference between the imaging and the treatment isocenter. So we call this the imaging treatment isocenter coincidence. So we can see the values, the trend, in which the uncertainty of the imaging versus treatment isocenter, it can be up to 0.6 mm, except one point where we measure it at 0.8 mm. This one after a year, so this is the value. So we can see that it has stabilized after during this time, but there are times when it exceeded, can be up to 0.8 mm. So this is something that has to be considered in the PTV margin for all the patients at the center. So if you put a rough figure of 1 mm uncertainty from the isocenter, so we can include that in the equation. So where the expansion of the CTV margin of x mm is consists of the uncertainty from the immobilization system, which I didn't put any in here, 0, as well as the 1 mm uncertainty from the isocenter. So it is the root sum square addition, where you square 0 and square 1 and then square root that to get the margin for the PTV. So moving next to the image quality test, I mentioned earlier, image quality of the cone beam CT system need to be performed monthly. So there are actually several image quality phantoms that we can use. And the most common one, even for CT imaging system, is the CAPFAN 600 phantom. So you can see the physical dimension of the uh, phantom here, and also the test modules that the phantom have for different aspects of image quality tests. And it also have a standard imaging parameters that you can use to image the phantom, and also you can perform qualitative or quantitative analysis of the resulted images to assess the noise and uniformity, the contrast to noise ratio, the CT number, the spatial resolution, and the geometrical distortion. And this is the same for the other phantom from CRS uh, company. So it has 4 test modules to cover uniformity, CT number linearity, low contrast, and spatial resolution assessment. So these are the test modules in the CAPFAN Phantom. Each of the test module have different test patterns to assess different image quality parameters of the imaging system. So CRS Phantom also have different test pattern to assess different components of the image quality test. You can see that this Phantom is also smaller compared to the CAPFAN Phantom, and also the length of the Phantom modules in total, they are also shorter compared to the CAPFAN Phantom. And this has the advantage of actually imaging the whole modules at the same time, compared to having the need to image the phantom in multiple imaging to cover the whole modules inside the phantom. So this video will show how we analyze the images we obtain from the CRS phantom using an in-house software that we develop in MATLAB environment. So we perform the analysis using a quantitative approach instead of looking at the images uh, visually. We actually analyze the pixel values on the images. So this is actually a semi-automated approach, because we still have to select the region on the images to be analyzed by to be in terms of the pixel values. So the first one is the image, the uniformity and noise analysis. So first we select the corresponding slices on the images that we obtain during Cone City imaging. So we have to bear in mind that we have to use the same imaging parameters for every test, and it should be also the same imaging parameters that we perform during acceptance testing. So once we have the uniformity images, we average these three slices, and then we select the horizontal region and also the vertical region on the on the images at the center of the phantom, and we plot the pixel value across it. So that is one method, and the other method is we actually select 5 points inside the phantom, as you can see at the center, and also at 4 points in the peripheral, and we get the mean pixel value of each of these points. So once we have selected all 5 points, we will get the pixel value for each point, and we calculate the uniformity index, the noise from this vertical and horizontal plot, as well as the integral non-uniformity that we obtain from the vertical and horizontal plot in the in-plane and cross-plane direction. So these are the values that we monitored monthly, and we compare that against the acceptance test value that we obtain. And next is the contrast and city number quantitative analysis. So again, we select the corresponding slices which have the points, which have the region containing different Hounsfield unit material. For air, LDPE, polystyrene, acrylic, Darwin, and Teflon. So we calculate pixel value inside of each of these region. So we get the mean and also the standard deviation of each of it, and also we measure the background of each of these region. So and then we can calculate the the contrast values based on this measurement and calculation. Okay, so that gives you the mean value for each of the uh, different materials, also the standard deviation value, and using that we can calculate the contrast to noise ratio as well as the city number, and we can plot the measured city number versus the theoretical city number to compare the constancy from month to month. Okay, and the next one is the spatial resolution analysis. Again, we select the corresponding slices that contain the spatial resolution test pattern. Okay, so this is the image of the spatial resolution test pattern that we got from the Cone City imaging system. So using qualitative method, so the physicist will observe each of these line pair sets, and you actually determine which of these set can be seen. So the highest spatial resolution that you can see on visually on the phantom, often we found that this is not it would be different from one person to the other, and it can vary depending on who's the one that is doing the evaluation. So that's why we come up with these quantitative methods, where we actually select each of these region on the phantom to calculate the line pairs per millimeter that can be uh, observed by the system. Sorry, that can be visualized by the system. So this is currently in this example is just for the uh, point of understanding the method, but actually in day-to-day QA tests that we perform at the institute, we actually automate this, and because the region will always remain at the same position on every imaging perform every month, so we automate this process, and we straight away we actually evaluate each of these line pair sets automatically without having to select each of the region. So we just select the images, and the result will be obtained automatically as this as a MTF plot that will be shown later. So this is the MTF plot, and we can record the values in terms of the spatial frequency at f50 and also f10. So we see the value that intersect at f50 and f10, which is 3.78 line pair per mm for f50 and about 6 line pair per millimeter at f10. So, and we record these values and monitor the changes as compared to the acceptance test value. The last test on CRS phantom is the geometric distortion. So first we load the corresponding slice of this test pattern. So we average the 3 slices, then we select the region having the marker. So there are 3 markers there. First the horizontal, vertical, and also the diagonal one in the other direction. And then we measured the distance from the 2 points using the peak value of each point. And then we compare with the specification, which is 55 mm here. This slide shows how the quantitative values measured every month changes over 6 month period for the uniformity, the contrast to noise ratio, the city number, as well as the spatial resolution. And this is a comparison between the values from CAPFAN versus the values from CRIS. Uh, we observe that the discrepancies between the two phantoms are there. This is mainly due to the differences in the size and the geometric design of the phantoms. So as we discussed earlier, CAPFAN is much larger compared to CRS. However, the results of image quality from the cone beam CT system do meet the manufacturer specification and also within the range obtained by the previous published values in the literatures. So actually we did this because at the beginning during commissioning testing, it was performed, the acceptance test was performed using CAPFAN Phantom. However, in our daily practice, we are using CRS Phantom because we don't have CAPFAN in our department. We had to borrow that from our imaging department every time that we want to do the test. So to transit from the use of CAPFAN to CRS, we actually did comparison study for over 6 months to see the consistency of the value over 6 months and benchmark that against CAPFAN Phantom. And after that, we start using the CRS Phantom value as our comparison for our subsequent monthly tests. So the next one is on gating. So there are also components that need to be checked when if you have a gating system on your Linux. So it's usually looking at the beam output constancy when you're using gating delivery. Also have to check the phase amplitude beam control, the respiratory monitoring, and also getting interlock to be functional. Of course, these are not extensive list of the tests that you need to do for gating. There are other references that you need to look into for such system. So on top of the monthly test, there's also the annual test. Usually annual tests are the subset of the tests performed during acceptance testing and commissioning procedures. And during this annual review of the dosimetry system, constancy factors are either established, reconfirmed, or updated. So, but in Malaysia, because we follow our requirement to have the test performed by an external QA test, which is licensed, usually from a QA consultant company. So usually medical physicist does not, in-house medical physicist does not perform this annual test, but they should actually be highly involved with during the test to ensure that all the annual QA components listed in the supplement are tested by the company, and any corrective actions required are performed by the linear engineers. So you cannot leave it done by the class H tester. You need to monitor what they do and also make sure that it is actually within the tolerance value that you expect. And if there's any discrepancy, it needs to be referred to the service engineer, the manufacturer, for corrective actions. So in summary, radiotherapy is a complex process. The treatment is delivered over many fractions. There are many changes that happens over time. It also involves different staff groups. So a single statement about accuracy requirements in radiation therapy is oversimplification. And the accuracy requirements are dependent on both the technological consideration as well as the clinical concerns of the center. So it is very important to understand the uncertainties of the system through quality assurance program, and that via good documentation and also staff communication. So with that, I would like to thank you all for listening.